Hi, I'm Tamanna here to present our paper Characterizing Mamba's Selective Memory using Auto-Encoders. This is joint work done between researchers at Dataminer and UCI. State-space models, or SSMs, are a promising alternative to transformers for language modeling because they use a fixed-size hidden state rather than growing memory with sequence length. But this fixed memory means the model must compress and inevitably lose some information when processing long sequences. While prior work has focused on when this information loss occurs, our work asks a different question. What kinds of information are lost in the hidden states of pre-trained Mamba language models? In this paper, we introduce a method for understanding which tokens and sequences Mamba is most likely to forget in practical settings. The idea is straightforward. We take input text with known properties such as part of speech, named entity token tags, and sequence level labels, and we compare them to reconstructions generated from Mamba's hidden state. By looking at reconstruction errors measured through F1 scores and token omission rates and relating those errors to labeled properties, we can see patterns in Mamba's selective memory. For example, in the figure here, the number 42 is reconstructed incorrectly as 57. To produce these reconstructions, we train an autoencoder that decodes sequences from hidden states created by a frozen pre-trained Mamba encoder. This allows us to study Mamba's recall of any text without needing to provide special memorization cues. We use model sizes ranging from 130 million to 1.4 billion and sequence lengths 4 to 256. To understand what types of tokens Mamba tends to retain versus forget in its hidden state, we look at tokens with the top omission rates in natural text and omission rates across part of speech and named entity categories in annotated data. To get a sense of which tokens Mamba tends to leave out when reconstructing natural text, we look at the pile evaluation dataset and measure omission rates for each token across all sequence length. This table shows the most frequently omitted tokens for the 1.4 billion model, and we see consistent results across model sizes. Among the top 50 omitted tokens, there are many numbers, individual letters, and common stop words. This gives us our first clue about Mamba's memory. It seems to have particular difficulty with math-related content, since numbers and letters often serve as variables or placeholders in mathematical text. To understand how well Mamba retains different parts of speech and named entities, we run experiments on the Connell 2003 test split. This dataset gives us 3,453 examples of English newswire text, and each token comes labeled with both its POS tag and its NE tag. To keep things consistent, we concatenate the examples until they reach a sequence length of 256, since this is the length where we observe the highest omission rates. To account for multiple comparisons, we apply a Bonferroni correction to adjust the p-values for all the comparisons we run using a significance level of 0.05. For parts of speech, we find that numbers have the highest omission rate across all model sizes. In the 130 million model, numbers are omitted 50.8% of the time, and even in the larger 1.4 billion model, the omission rate is still 22.7%. We also see a statistically significant difference between numbers and every other POS category for both models. Taken together, these findings strengthen the earlier conclusion that Mamba's hidden state consistently struggles to retain numbers. For named entities, we find that organizations have the highest omission rate across model sizes. In the 130 million model, organizations are omitted 35.8% of the time, and in the 1.4 billion model, the omission rate drops but is still 12.3%. We also observe a statistically significant difference between organizations and the other named entity categories, indicating that Mamba tends to struggle most with retaining organizational entities. Next, in order to understand what types of sequences Mamba tends to retain versus forget in its hidden state, we look at reconstruction fidelity across different subsets of pile and different dialects. To understand how well Mamba's hidden state preserves different kinds of information, we look at reconstruction performance across a wide range of textual domains. We sampled 700 sequences from 9 subsets of the pile. These cover everything from web text and scientific writing to code, legal documents, and mathematical content. Across model sizes, we see a clear trend. Reconstruction quality deteriorates the most for mathematical data as the sequences get longer. For the 130 million model, the DM mathematics subset has an F1 score of 99.9 at a sequence length of 4, which is essentially the same as the other domains. But when we move to sequence length of 256, performance of DM mathematics drops sharply to an F1 score of 41.6, while other domains remain noticeably higher. For example, Common Crawl still achieves 69.7 at the same length. The other subsets stay relatively close to one another without this dramatic decline. These results reinforce what we saw in the token level experiments. Mamba's hidden state has particular difficulty retaining mathematical information. To test whether dialects affect how well Mamba retains information, we used a pair dataset, which provides parallel sentences in African American Vernacular English, or AAVE, and Standard American English, or SAE. As before, we concatenate each instance to a fixed maximum length ranging from 4 to 256 tokens. For shorter sequences, reconstruction quality is very high and almost identical for both dialects. With the 130 million model at a sequence length of 4, SAE reaches an F1 score of 99.7 and AAVE is virtually the same at 99.6. But as the sequence length increases, a performance gap begins to emerge. By the time we get to sequences of 256 tokens, SAE reconstruction drops to 65.3, while AAVE falls even further to 59.7, creating a noticeably larger difference. We observe similar trends across model sizes, suggesting a consistent pattern. Mamba's retention appears to degrade more for AAVE than for SAE as sequences become longer. To understand why certain tokens and sequences are more likely to be omitted by Mamba, we take a closer look at its training data. We start by sampling 200,000 instances from Pile. We then annotate these samples using a POS tagger. What we find is striking. Numerical tokens have the lowest count per unique token of all categories we analyze. In contrast, determiners, which have some of the lowest omission rates, show the highest count per unique token. This reveals a clear pattern. Tokens that appear less frequently during pre-training tend to be omitted more often, suggesting a strong link between omission rates and pre-training frequencies. To get a clearer picture of how numeric information is being distorted, we look at the character level deviations in Mamba's reconstructions. We compute the Levenstein distance between incorrectly generated numeric tokens and their true references on both the Connell 2003 and Pile evaluation sets. Across datasets and model sizes, the median reference number is only 2 to 3 characters long, yet the median edit distance is 2, meaning that most characters in the generated numbers do not match the original. To understand how large these deviations are in terms of value, we extract the numeric tokens and compute the mean absolute percentage error, or MAPE. This metric lets us compare errors relative to the size of the number, so it's a scale-independent measure. On the Connell 2003 test set, the 103 million model produces numbers that differ from its originals by 8.4 times their magnitude on average. As model sizes increase, this improves. The MAPE drops steadily and reaches 1.9 for the 1 billion parameter model. When evaluated on the Pile dataset, MAPE grows with chunk length across model sizes, starting at 0 for sequences of length 4 and rising to 38.2 at a chunk length of 256. Overall, these results show a clear pattern. Larger models preserve numeric magnitudes better, but longer sequences cause numeric values to degrade severely. In summary, in this work, we set out to understand what kinds of tokens and sequences Mamba language models are most likely to forget. A key result is that Mamba LMs consistently struggle with certain types of information, especially numbers, and this behavior appears to be influenced partly by how often these tokens occur in the pre-training data. Beyond empirical findings, we also introduce a general framework for diagnosing memory limitations in models with fixed-size hidden states. Since large language models are often used as black boxes, having tools that reveal where their memory breaks down is an important step towards ultimately improving their reliability. We make our framework available to be used for future work into SSMs and other related architectures. Please check out our paper for further details and feel free to contact me at any of these platforms. Thank you.